Ever wondered how your computer processes strings of data? Well, that's where string instructions come in. These are the building blocks that allow our computers to handle and manipulate data strings. Now you might be asking, what exactly are strings of data? In layman's terms, a string of data is simply a sequence of characters, numbers, or symbols. They form the basic elements that your computer uses to process and store information. From the words you type into a search engine to the code that programmers write, they all comprise strings of data. But here's where it gets interesting. To manage these data strings, our computers use something called assembly language. This is a low-level programming language that communicates directly with the hardware of a computer. It's like the secret language that your computer's processor speaks. And within this language, there are special commands known as string instructions that perform operations on these strings of data. String instructions, also known as string manipulation instructions, are an integral part of assembly language. They are designed to efficiently perform repetitive operations on sequences of bytes, which are typically strings of data. These instructions allow our computers to carry out tasks like copying strings, loading strings into memory, comparing strings, and so much more. One of the most fascinating features of string instructions is their association with the rep or repeat prefix in the context of x86 assembly language. This prefix enables the computer to repeat a string operation until a specified condition is met, making tasks like searching within a block of data or text manipulation incredibly efficient. So why are string instructions so important? Well, without them, our computers would struggle to handle the vast amounts of data they process every day. They are the unsung heroes, making it possible for us to use our computers for everything from writing emails to developing software. In the next few minutes, we will delve into the fascinating world of string instructions, one step at a time. So buckle up and get ready for a journey into the heart of your computer's processor. First up, we have the movs instruction. Now, the movs instruction, or move string, is a bit like a diligent postman. It's all about moving data from one location to another. It copies a block of data, often used for duplicating strings, and shifts it from the source to the destination. Take a look at these examples: movsb, movsw, and movsd. Each of them represents a different size of data to be moved. movsb moves a byte, movsw moves a word, and movsd moves a double word. The source of the data is always at the memory location pointed to by the source index, or SI, and the destination is the location pointed to by the destination index, or DI. Imagine you're a composer and your data are the notes. The movs instruction helps you rearrange your symphony, moving notes around to create a harmonious melody. As you can see, movs is a versatile tool for manipulating strings of data. Now let's move on to the LODs and STOS instructions. In the realm of x86 assembly language, the LODs and STOS instructions play crucial roles in string manipulation. Starting with a LODS, which stands for load string, this instruction is responsible for fetching data from a source string and loading it into a register known as the accumulator. The accumulator, depending on the specific LODS instruction used, can be AL, AX, or EAX. For instance, the LODSB instruction loads a byte from the source string located at the SI register into the AL register. Similarly, LODSW and LODSD load a word and a double word respectively from the source string into AX and EAX. This series of operations is essential in preparing data for further processing or manipulation in our programs. On the other hand, we have the STOS instruction, which is the abbreviation for store string. It does the exact opposite of the LODS instruction. It takes data from the accumulator and stores it into a destination string. Just like LODS, STOS also comes in 3 flavors: STOSI, STOSU, and STOSID. STOSB takes a byte from the AL register and stores it into the destination string at the DI register. STOSU and STOSD work in the same fashion, storing a word from the AX register and a double word from the EAX register into the destination string respectively. Imagine a scenario where you've loaded a string of data into the accumulator using the LODS instruction, performed some operations on it, and now you want to store the result back into a string. That's where the STOS instruction comes into play, effectively completing the cycle of loading, processing, and storing data. In conclusion, LODS and STOS are 2 sides of the same coin. with one loading data from a source string into the accumulator and the other storing data from the accumulator into a destination string. They're fundamental instructions that form the backbone of many operations in string manipulation. LODs and STOS are fundamental instructions for loading and storing data in string manipulation. Next up, we have the CMPS and SCAS instructions. Let's explore the CMPS instruction first. Standing for compare string, CMPS does precisely what its name suggests. It compares two strings and sets the flags accordingly. Imagine you have two strings, one at the source index, the other at the destination index. The CMPS instruction will compare the two, byte for byte, word for word, or double word for double word, depending on the specific variant of CMPS used. For instance, CMPSB compares a byte at the source index with a byte at the destination index. If you have two bytes, one at each index, CMPSB will compare them and set the flags based on the result. CMPSW and CMPSD work similarly, but they compare words and double words, respectively. Now, let's turn our attention to the SCAS instruction. SCAS stands for scan string, and it's used to compare a string with a single byte, word, or double word. Unlike CMPS, which compares two strings, SCAS compares a string with a single element. Take SCASB, for example. This instruction scans a byte at the destination index and compares it with the byte in the accumulator. If the two are equal, SCASB will set the 0 flag. If not, it clears the 0 flag. SCASW and SCASD function in the same way, but they compare words and double words respectively. So what's the point of these instructions? Well, they allow us to compare strings and single elements quickly and efficiently. Whether you're checking if two strings are identical or if a string contains a specific element, CMPS and SCAS have got you covered. Remember, these instructions are just tools in your toolbox. They're powerful, but their power lies in how you use them. With a good understanding of CMPS and SCAS, you can write efficient, effective assembly code that can handle a wide range of tasks. With CMPS and SCAS, we can easily compare strings and single elements, setting the stage for complex operations. Last but not least, let's discuss the rep prefix. To put it simply, rep stands for repeat. As you might guess from its name, the rep prefix is used to repeat the operation of the string instruction that follows it. But the repetition isn't mindless. It continues until a certain condition is met, making it a powerful tool in the programmer's arsenal. So how does it work exactly? Let's consider an example. Suppose we have a movsb instruction, which moves a byte from the source string to the destination string. If we prepend this instruction with the rep prefix, the operation will be repeated. But how many times? The answer lies in the CX register. The rep prefix uses the value in the CX register to determine the number of repetitions. After each operation, the CX register is decremented by 1, and the operation is repeated as long as the CX register is not 0. But rep isn't a one-trick pony. It comes in a few different flavors, each adding a conditional twist to our repetition. There's repi, which stands for repeat if equal. Here, the operation is repeated until the CX register becomes 0, or until the 0 flag is set. This is typically used after a compare or CMPS instruction to repeat the operation until two strings are found to be equal. Then there's repni, which stands for repeat if not equal. It's the rebellious sibling of repe doing the exact opposite. The operation is repeated until the CX register becomes 0, or until the 0 flag is not set. It's commonly used to scan, or SCAS, a string until a specified value is found. In essence, the repi prefix, along with its variants repi and repni, provides a robust mechanism to control the repetition of string operations. It allows for efficient iteration through strings and blocks of memory, making it a vital tool in text manipulation and searching tasks. The rep prefix adds another dimension to our string manipulation toolkit, allowing us to perform repetitive operations efficiently. So, there you have it. A crash course in string instructions. We've delved into the roles and functions of each string instruction. We uncovered the movs instruction's ability to copy blocks of data, and the LODs and STOS instructions' roles in loading and storing data from and into strings. We also shed light on the CMPs and SCAS instructions, which play a crucial part in comparing and scanning strings. Lastly, we discussed the rep prefix, a key player in repeating operations until certain conditions are met. These instructions are not just lines of code, They are the backbone of many operations in computer programming. They allow us to manipulate, compare, and process strings of data with efficiency and ease. With this newfound knowledge, you're well on your way to understanding the intricacies of string manipulation in computer programming. Thank you for watching.